the timer for the first question if you haven't answered it yet. Obviously, this is a little unusual, so we're going to be doing questions in the chat. If you have a question, put up your hand in the chat and I'll try to stop. And also, there'll be some Top Hat discussion questions that you can answer questions in, or ask questions rather. So we'll try it and see how it goes. Okay, so the other thing that I should tell you is there is a delay. I've tried to put it on the lowest possible delay, but it's still like 15 or 20 seconds. So there might be a little bit of issues with being out of sync, but we will try our best and see how it goes. So yeah, let's get started. So let's see how you guys did with this question. We have a 3x3 matrix. This is review from last time. So I don't know if you can see my mouse here. This is the 3x3 matrix. I told you it's eigenvectors and eigenvalues, saved you a lot of time here. And we're asking about the long-term solution. Let's see what people said. 76% of people think option C is correct. Some solutions blow up and some solutions tend to the origin. That is correct. That's the right answer. So what's going on here, and probably you figured this out since most people got it right, is that the solution, you can write it like this: C1 V1 e to the lambda 1 t plus C2 V2 e to the lambda 2 t plus C3 V3 e to the lambda 3 t. That's any solution. And the point is that in this problem, lambda 1 and lambda 2 are negative. So these two first terms are going to 0. But this last term is positive. Lambda 3 is plus 1. And that means that this is blowing up. All right, going to infinity. It's a vector though, so you got to make sure you know what you mean by going to infinity. So this is blowing up. This is, I guess, vector 0. So you have these two terms that are either going to 0 or blowing up, and depending on how these are combined, some solutions blow up and some solutions tend to the origin. So that is that question. Probably you can guess what the follow-up question is going to be here, which is going to be which of these solutions go to 0. So before we do that one, let's get a little quick check on the stream. So the next Top Hat question is, how is the stream working for you? How is that first little explanation? Is the sound working? That kind of thing. So I'll give you guys maybe a minute to do this. Do we need a timer? Let's put one in anyway. Okay, most people have answered. Probably we'll stop before we get to 0 here. A few stragglers at the end. Okay. I think I'm going to stop this timer now. Everyone's answered? Okay, and let's check out how you guys are enjoying the stream so far. Okay, it seems to be working for people. So again, feel free to use the chat if you have a question. I'll stop, and there'll also be Top Hat moments to stop. Okay, so follow-up question. We're going back to this problem, and the question is, which solutions blow up? Which solutions go to 0? Can you describe the set of initial conditions? So that's going to be the question we're going to do now on Top Hat. Describe the set of initial conditions x0 for which the solution x of t does not blow up. So for what solutions does it go to 0? That's the question. Okay, there's like 20 seconds left for me. By the time you hear this, there'll probably be less than 20 seconds left. All right, let's see the responses here. So most people think it's a plane, 56% of people. That is the correct answer. So let's see how this looks if we look at the algebra. So we had these two solutions. If you plug in t equals 0 to see what the initial condition was, what do we get? X of 0, C1, V1, and e to the lambda t, t is 0, that's just 1, so that doesn't do anything. Then we have C2, V2 plus C3, V3. So this should remind you of linear algebra class. We have three vectors, V1, V2, V3, and we're doing linear combinations of them. But the point is that as long as C1 and C2 are non-zero, those are the things going to 0. And if C3 is non-zero, that's the thing that's blowing up. So if it doesn't blow up, if solution doesn't blow up, we need C3 to be 0. So when C3 is 0, the only term in the equation, this last term that's blowing up because of the positive eigenvalue, when C3 is 0, that term goes away, and we're left with these two terms. So when C3 is 0, the solutions look like, at time 0, C1 V1 plus C2 V2. And this should remind you from linear algebra class, this is the equation of a plane. So as long as you start in this plane, which is spanned by these two vectors V1 and V2, the two eigenvectors of negative eigenvalue, lambda 1 and lambda 2, or both minus 1, which is negative. So as long as you start in that special plane and C3 is exactly 0, then you are sucked in. You only have this going to 0 part. The solution goes to the origin. As soon as you have a non-zero C3, if you're off this plane, if you're above or below that plane, then you have this exponential term that's blowing up. That's going to take you to either plus or minus infinity in some direction. And so in fact, this is a textbook example. So this is a textbook example from section, this is in the textbook in section 6.3, I believe. So you can check on that there too. And they really do it from scratch. They start with the matrix and get the eigenvalues and eigenvectors. But I'll show you now a picture of what this looks like from the textbook. So this is the textbook solution. Unfortunately, I can't zoom in anymore, so we're going to have to do it small. And you can see what's happening is there's this special plane S. S is this plane. This is what they're calling S. The span of the two vectors we saw, they call that S. This thing right here, they call that the plane S. And if you start in S, you get sucked in towards the origin along that plane. But if you are above the plane S, you get blown up away in this V3 direction. If you're below the plane S, you get blown away the other way. So there's sort of this explosion in the V3 direction, and in the V1 and V2 directions, you're shrinking in. Okay, that's the first example we're doing today. Today is really, I'm trying to do the simplest thing I can think of, which is to start with 3 textbook examples and see how this streaming thing works. So that was the first one. That was section 6.3. Finishing up from last time. And then we're going to jump into 6.4, which is complex eigenvalues. So that's what we're going to do next. But maybe we'll take a short little top hat pause here and see, are there any questions about this warm-up problem? So this is your chance. You can put in a discussion question. You should also be able to upvote other people's questions if you think there's a good question. If there's a question about the stream or something too, you can ask now. A lot of people are saying no. I guess that's good. I think you don't have to answer this if the answer is just no, but I mean, feel free. I'm not going to stop you. Let's order by most liked. This one is interesting. It says new. Let's find that one. Oh, I missed it. Okay. The delay makes it difficult to answer top hat. Okay, I'll try to give more time on top hat to try to account for the delay. Yeah, let's upvote that. Will the recordings be available after? I believe they should be on YouTube, so I did a test yesterday, and it automatically posts them. So as long as that works the way I think it does, they will be available after. So maybe let's upload that as well. Yes. So they should be available. Can I see what you were again? I don't know what that means. Maybe that means you want the paper. I don't know. This is the paper. Is the plane S composed of the vectors that sync to the origin? So the question was, is it always composed of the vectors that sync to the origin? So I would say the plane S is spanned by the vectors, the two eigenvectors that are negative. So you can, the way you would generalize this problem is you take all the eigenvalues that are negative, you take their vectors, and the span of those is some kind of plane or line or something, and if you start there, you always go to 0. The things that have positive eigenvalue, as soon as you have a little piece of those, so as soon as the coefficient is non-zero, then you're blowing up in some direction or the other. So that is the answer to the question about, is the plane S always composed of vectors that sync to the origin? Okay. I think that's it for the questions. So we are going to start with, now we're going to do another textbook example, which is one we've seen already, and I promised we would work on, and it's the mass spring system. So I'm going to put this paper away now. I've got a new piece of paper. So we were working on this mass spring system, and the point was we worked really hard. We added up forces and so on, and we got the matrix for this equation. So remember, we had a vector which had 4 components, x1, x2, x3, and x4, which were all functions of t. So normally we don't write that, but let me write it right now to see what's going on. And we made those equal to the positions and velocities of the blocks. So there's y1, y2, and then there was y1 prime, y2 prime. So the first 2 components are position, the second 2, so first two components are positions of blocks, and the second 2 components are velocities. Okay, and the point was, if you have the positions and the velocities, you can write down a differential equation for how this is working in terms of itself, and that was a 4x4 matrix. So this, if we call this whole thing x, I should have maybe called that vector x. It's this thing, we got the equation that vector x prime is equal to, and we found this big 4x4 matrix last time, times vector x. So it's a 4x4 matrix. So here, let me divide it up into the 4 slots here. So let me see, what was the matrix? I'm just copying it down from my notes from last time. 0, 0, 1, 0, 0, 0, 0, 1. So if you remember, these first 2 rows actually just tell you that the first 2 components, y1 and y2, are positions, and the second 2 are velocities. So this just keeps track of the derivative of the first 2 things should be the third and fourth component. That's what the zeros and ones in the first 2 rows did. And then the second little bit, the last 2 rows, actually contain the physics of what's going on here, and that was this combination with the spring constants k1 and k2. So it was minus k1 plus k2 divided by m1. And over here it was k2 divided by m1. Or was it divided by m2? Divided by m2, 0, 0. And this was k1, k2 divided by m2 again. And this was minus k2 plus k3 divided by m1, 0, 0. So that's what I have in my notes from last time. We also, if there's external forcing, it looks like this: 0, 0, f1 divided by m1, f2 divided by m2. So that should be all review from last time, where we figured out what this matrix was. Now we're going to analyze it and see what it tells us about the solution. So that's what we're going to do now. And the first thing you got to do is you got to find the eigenvectors and eigenvalues. And like I said, we could spend a lot of time going through the 4x4 determinant to figure out what are the eigenvalues of this matrix, find the characteristic polynomial, and so on. But I'm going to tell you what the characteristic polynomial is. for these things because you should have done that in linear algebra already. So if you do some math, and there's some nice ways to do it using tricks about block matrices and row operations. So you can do this 4x4 determinant because it's easy to do because it has lots of zeros. And if you calculate that, you'll get that the characteristic polynomial of this matrix is, what is it? Okay. There's one other thing I'm going to do to make things simpler, just so there's less to write, is we are going to look at a special case today where K1 and K3 are both 1, and K2 is some arbitrary constant we're going to call K, and M1 and M2 are also both 1. So if we go back to the picture here, so what does that mean? The middle spring in the system is free, that's the K, but the springs on the outside are always 1, and the masses are both 1. So that's just going to simplify our algebra a little bit. We could do it in full generality. It wouldn't change the problem really at all, but it would just be more annoying to write down. So that's already complicated enough. So that's what we're doing here. We're setting the middle spring, so this is the middle spring, to K, and we're setting the outside springs to 1. And these are the masses. And we're doing no force. So F, and we're going to do F1 equals F2 equals 0. So no external force, just the springs on their own. Okay, if you do these things and you calculate the characteristic polynomial, you get P of lambda. It has a nice form. It's lambda squared plus 1 times lambda squared plus 1 plus 2k. So a nice thing, product of two quadratic equations. So it's a fourth order polynomial, but it's a product of two quadratics like that, which is nice and simple. Okay, so from this, you should be able to find the eigenvalues, and that's easy. That's the roots of this thing. So that's what I'm going to do now. So find the eigenvalues. And again, feel free to stop me if you have any questions. Somebody said it's difficult to read the subscripts, which is very good. So that is also part of the reason I got rid of K1 and K2. There's no more subscripts anymore. So hopefully after this page, there will be no subscripts. So that, we'll see how that works out. And yeah, I can also try to write a bit bigger. If you think I should maybe write less on a page, then you could put that in the comments as well, and I could try. I don't know what I'm doing. This is my first time, but we're trying our best. Okay, find the eigenvalues. Those are the roots of the characteristic polynomial. So P of lambda equals 0. But P of lambda was a product of two things. So one of those two things better be 0. Lambda squared plus 1 equals 0, or lambda squared plus 1 plus 2k equals 0. Yeah, and I can also post these pages after if you guys are interested in that. Okay. So those are the two possibilities. This gives something that's going to happen that you've seen before, which is that the eigenvalues don't just come on their own, they come in pairs. So the eigenvalues from this part of the equation, lambda squared plus 1 equals 0, that means lambda is either I or minus I. So we've seen that before, I and minus I. That's I's evil twin. They come in pairs. Over here they also come in pairs. So lambda is I times the square root of 1 plus 2k, or is equal to minus I times the square root of 1 plus 2k. And so this is the thing that will always happen in these equations, is if you have imaginary eigenvalues, they can never come on their own. They always come in pairs. And we're going to see how that plays out, too, in what happens for their behavior later. Okay, so the eigenvalues come in pairs I and minus I. And now what I'm going to do is I'm going to find the eigenvectors. So this is more of like what we did last time of finding the eigenvectors in the 3x3 case, except for now there's complex numbers. And that makes it a little bit more scary, but it's the same kind of thing as before. So we're going to do that now. So find eigenvectors. And I'm going to start with the eigenvalue lambda equals plus I. We'll find that first. So in principle, you have to do all four of these separately on their own. But we'll start with this one. So what I'm going to do is I'm going to look at the matrix. If the matrix was called A, so that 4x4 matrix we had, we're looking at A minus lambda times the identity. And we're looking for solutions to this V equals 0. Okay, so if you take that matrix, you subtract minus lambda times the identity. Lambda is I, so we're subtracting I from all the diagonals. What are we getting? Minus I, 0, 1, 0, 0 minus I, 0, 1, minus 1 plus k, k minus I. Oh dear, I think I've botched this matrix. So this is supposed to be a 4 by 4 matrix, and I drew the minus 1 plus k sort of taking up the first two columns. So I think this whole matrix is garbage now. We gotta start again on a new page. So on a chalkboard, it's not so bad. You just rub it out, and everyone will forget that you made a mistake. But on paper now, it's here forever. Very embarrassing. But we'll try our best anyway. Okay, let's try this again. So a minus lambda I times the identity, and lambda equals plus I. So we're taking the matrix from before, and we're subtracting I from the diagonal. So let's try that one more time. 4 by 4 matrix. So that is why I think it helps to divide the matrix up a little bit before you start. So minus I on the diagonal. And I think this matrix had zeros on the diagonal originally, which makes it easy. And now I just got to copy over the rest of the matrix. So there was 1, 0, 0, 1 in the first two rows like before. And then on the bottom two rows, there were things involving K1, K2, M1, and M2. But I simplified those a bit. So remember, K1 and K3 are 1, and K2 is just K. M1 and M2 are 1. So that's why it's coming out a little simpler here. There's minus 1 plus K, and K, and minus 1 plus K in this corner, and over here there's zeros. Okay, so we're looking for solutions times this thing times A, B, C, D to be 0. And if you look at the first two rows are very nice because they only have two things in them. They have minus I and 1 and minus I and 1, so they're kind of connecting A and C and B and D. So from the first two rows, you get this nice relationship that C is equal to I times A, and D is equal to I times B. So if you expand this out, minus A plus 0B plus C plus 0D, and just rearrange it, you get C equals IA. And so that's from the first row, and from the second row, you get D equals IB. And you know, it's not a coincidence that this is happening. The first row in these kinds of physics problems is always the same, because the first row, remember, it just came from our definition. The first row came from the fact that the third component is the velocity, the third and fourth components are the velocities, and the first two components are the positions. So as long as you have this same setup, when you do your eigenvalues and eigenvectors, it's always going to come out this way. So we'll see we'll see more of this in a minute too. We'll see another way to think about that. But the first two rows are boring. The last two rows are where all the physics action is happening. So I'm going to expand out what this third row says. And I think it says minus 1 plus K times A plus K times B minus I times C equals 0. So there's 0 times D. There's no D's. Okay, but I times C is something nice, because if C equals IA, then I times C is I squared times A, which is minus A. So this thing is actually a minus A. And this means if you rearrange it, there's a minus A here, and there's a minus 1 plus K A. So what are we going to get? I think we're going to get, so just being careful with the minus signs. This is a minus KA with a minus 1, and then I have a minus A, which is a plus 1, so the plus 1 and the minus 1 cancel. So making sure you don't screw that up. And that's very easy to do when these i's are floating around. Minus KA plus KB equals 0 is the equation I get. Minus KA plus KB equals 0, this is a nice easy equation that just says A equals B. Great. Let me pause for a second to make sure I'm not doing something wrong here. Yeah, so I always get tricked up by these I squareds and the minus ones. It's easy to screw something up. Okay, so that's A equals B. What does the fourth equation say? So this was the third. These are the first two equations. First two first two rows. This is the third row. So if you remember how everything has been going, when we find eigenvectors, you will know that the fourth row doesn't contain any extra information. So the fourth row is identical to everything we've done already. The fourth row is not an independent equation. There's a redundancy here, and so we are expecting to find something like this, a relationship at the end of the day, that something like A equals B. So the fourth row has no new information. Okay, so what does that mean? A possible eigenvector. What are the possible eigenvectors? It's anything where A equals B, where the first two components are 0, and where the second two components, C and D, are equal to I times A and B. So one example, you got to pick your favorite example where the first two components are equal. One possible thing is 1, 1. So make the first two components equal. The third and fourth components are I times the first two, so I. So there you go, we found the eigenvector. So that was all this work for the lambda equals plus I eigenvector. So now we got to do it 3 more times. And I'm going to let you guys do this on top hat. So we're going to do lambda equals minus I next on top hat. Is there a shortcut? This is the question. Do we have to do the whole calculation from the beginning over again, or is there some kind of shortcut? I'll give you guys I'll give a little extra time here because of the delay, so you guys can have a chance to work on this one. Okay, and again, good time to ask questions while I'm sitting here if you want to put something in the chat. Can you show the page? Yes, I can show the page. Absolutely. Yeah, in fact, you guys can see top hat, so you don't need to, I don't need to show that. Okay, almost everybody has answered. I don't think I'm going to do a timer. I'm just going to stop the top hat in a second here. 3 people haven't answered. Who do we contact for midterm questions? So there is a regrade thing posted on Quarkus. How am I doing today? And nice painting. Thank you on both counts. I am doing good. Okay, I'm going to stop this question now. Let's see how you guys are doing. Close. Responses. You guys are great. Normally we do these 98% things everyone's wrong, but today everybody is right. There is a shortcut. It's a very easy shortcut. Remember, I and minus I are evil twins of each other, so the eigenvectors will also be evil twins of each other. So let me get another piece of paper here to get this one down. So for lambda is I, the solution was 1, 1, I, and for lambda equals minus I, the solution is 1, 1. And all you do is every time you see an I, you replace it with a minus I, minus I, minus I. Okay, so we've figured out sort of half the solution so far. So the general solution is going to be, x of t is going to be c1 v1 e to the lambda 1t plus c2 v2 e to the lambda 2t plus, and then over here there's lambda 3, lambda 4 stuff. We'll get to that in a minute. So we've sort of done the first half of this whole thing. It's 1, 1 I times e to the it plus c2 times 1, 1 minus I times e to the minus it plus the lambda 3, lambda 4 stuff. So I'm not going to focus on this right now. We're going to do this in a minute. This stuff should look very, very familiar to you from the second order equations that we did in chapter 3 and 4. So in fact, I really think that for every eigenvalue pair you have, so I and minus I, it really is a total copy of what we did in the earlier chapters. You have the two vectors, v1 and v2, are complex conjugate pairs of each other. So v2, some people will write v1 bar, right? They come as evil twins of each other. The lambdas come as evil twins of each other, lambda 1 and lambda 2. So this whole thing should remind you a lot of what we did before. I'll say one other thing, is that it's not a coincidence that this is 1, 1, I. The positions, the first two columns are positions. So from this page, the first two columns are positions, the second two are velocities. So if you read the first column here, this is saying y1 is equal to e to the it. So if y1 is e to the it, this 1 times e to the it, then what is the third component, its derivative? Y1 prime is I times e to the it. So the first and third thing are linked because they're derivatives of each other. And so that's why you always get a multiplying by I down here. And so in general, it's going to always be something of the form, for example, it would be 1, 1, lambda, lambda times e to the lambda t. Whatever is coming out as a velocity is always the eigenvalue lambda times the whatever is in the position. So this was the same thing in the second order equations. I really think this whole chapter, this part of the chapter, understanding what's going on, if you understood third order, chapter 3 is the second order equations. Chapter 3 is 2 by 2 things. So if you understand 2 by 2 systems and second order equations from chapters 3 and 4, this is all a repeat of that. Okay, so that's that. There's one other thing you can do with this, which is instead of writing it in terms of e to the it and e to the minus it, you can write it in terms of sines and cosines. So that's the last thing I'll do here. And you can already do it just on this piece. So you can sort of think of all the pieces as being separate and put them together at the end. So that's what I'm going to show you now, is that you can convert this piece that we've done into sines and cosines and not worry about this stuff yet. Okay, so let's do that. So I claim that if you have C1 times 1, 1 I plus C2 times 1, 1 minus I, this is all times e to the minus it, this is all times e to the it. Okay, there's going to be other stuff here, but we're going to ignore that for now. This is the solution x of t. So you can write this in terms of sines and cosines, just like we did before. So very technically speaking, what we're doing is plugging in like C1 is a half, C2 is a half, that whole thing. But because of that theory, we know that we can take the real part and imaginary part of either of these and use those as a basis of a solution. So you could also write this as C1. Okay, I shouldn't use C1 because it's not exactly C1. So let me give it a different name. Let's call it capital C1. Capital C1 times the real part of this whole thing, 1, 1 I times e to the it, plus capital C2 times the imaginary part of this whole thing, 1, 1 I e to the it, plus the other stuff. So this is something that just carries over from chapter 3 and 4, this whole thing about taking the real and imaginary part of any particular one of these pairs. That works as a valid basis for the solutions. Okay, so let's figure this out. Here it's going to be sines and cosines because of Euler's formula. So this is a C1, and then you have cosine t from the 1 times e to the it. I times cos plus I sine. I think these are minus signs. And you can always check if you're right because these are supposed to be the derivative of those. So you got to do the derivative. The derivative of cosine is minus sine, so that works. Okay, C2. Over here we're doing the imaginary part, so I think I get sine of t, and cosine of t, plus the other stuff. Okay. So one way you can write this is as linear combinations of sine and cosine. So you can do that right now. So C1 cosine of t times 1, 1. Okay, I screwed this up. Let's try this one more time. So what I want to do is I want to collect the cosines and the sines. Let me try that again. So I'm going to put cosine of t over here. What is in front of cosine of t? There's a c1 and then 1, 1, 0, 0. That's this guy. Plus a c2 times a 0, 0, 1, 1. And then you can write it like this. You know, I'm looking at this right now, and I'm thinking this writing right now is not helpful for what we want to do. So I think let's just scrap this for now. You can rewrite it like this in terms of factoring out the sines and cosines, and sometimes that's useful. But I think I'm just going to leave it the way I had it on this page up here and leave it like that. So what have we done so far? We did one of the complex conjugate pairs. We did I and minus I. And we figured out the eigenvector. We wrote it two ways, with the real and imaginary part, which is purely real, and in the complex exponential part. So this part is like mathematically convenient, but is not useful at all for analyzing what's going on. This part is a lot nicer. So sometimes it's a lot easier to write it like this. Okay, that was all for the pair I and minus I. There is one other complex conjugate pair of eigenvalues. Where did it go? Here it is. The pair I times the square root of 1 plus 2k and minus I times the square root of 1 plus 2k. So we're going to have to figure out the eigenvectors for that and do the whole thing again. And you'll see actually there's a nice interpretation at the end of it. So I'm going to let you guys do this one in Top Hat. Okay, and I'm realizing in Top Hat I didn't do what I thought I was doing. In Top Hat, I asked you guys to find the components of the eigenvalue lambda equals I, which is the one I did. So this is a typo. So what you should do in Top Hat, and I'll write it down for you here, is we want to do the other eigenvalue. So we want to do lambda equals I times the square root of 1 plus 2k. That's what we want to do. So do that one in Top Hat. If you tell me 1, 1, that's the wrong answer. Okay, so we're doing this eigenvalue. What is the eigenvector? And I'll give you a minute to start working on this. I'll write down the equation to start as well. That might give you a head start. So you always start with a minus lambda I times the identity equals the 0 vector. So that's what we're doing. Okay, you got to be careful here because 1 plus square root of 2k takes up a little bit of space. So we got minus I times the square root of 1 plus 2k. 0. Those are the first two rows. And now things get a little extra hairy. These last two rows. So that's the system you got to solve to find this eigenvector. Okay, so this one is harder than the last one because you have these square roots are floating around and they make things a little bit annoying. But the math works out really nicely at the end, so you should get a very simple answer at the end. Okay, I'm going to start, working on this one a little bit. So the first two rows are something simple again. C equals I times the square root of 1 plus 2k times A, and D equals I minus plus I. Times B. So I think I've unpackaged the first 3 rows. If you do the matrix multiplication, you get these 3 things. And these 3 things together, if you just carefully do the algebra, will lead you to the answer here. Okay. In the top hat, I'm only asking for the first 2 components. So I'm just asking for A and B. Okay, maybe I'll do one more step here. So I'll just plug in that C is I times the square root of 1 plus 2k times A. And you'll see this is where the nice thing happens. Even though there's square roots, when you plug this in, the square roots multiply each other and go away. So after one more step, 1 plus k times A plus k B minus I times this stuff times plus I times this stuff. So I squared is minus 1. So you get a minus 1 times 1 plus 2k A equals 0. And so if you just take this last one and rearrange it, so you got to carefully do the cancellations, make sure all the pluses and minuses are right. That's what I'm asking you to do in top hat. So I think only 64 people have answered. I'm going to leave it for 30 seconds or a minute here and let you guys finish it off. How are A and B related? Those are the first 2 components. Someone is saying they don't see the new question, so it's the thing that's been in top hat for a little while now. It says, what are the first 2 components? And there's a typo in the question. So the question says lambda equals I, but I really want you to do this other one. So I did half of it at the beginning. Now I'm asking you to do the other half. So we're doing lambda is I times square root of 1 plus 2k. Someone asked, will the 4th row in the matrix just produce the same relationship of the 3rd? Is that why we skip it? Yeah, that's right. So the 4th row is sort of redundant. Okay. We're up to 104 people have answered out of 114. So I'm just going to wait like 10 or 15 more seconds, and then I'm going to stop it and see if you guys are able to figure this out. So finding the eigenvector here. And then the last little bit, we'll interpret what's going on here. Okay, I think I'm going to stop this now. I'm going to stop the top hat. Let's see if people figured it out. Lots of people said 1 minus 1. That's the right answer. So if you, hopefully, if I didn't make any typos here, on paper, if you rearrange this, you've got a minus k over here, you've got a plus 2k over here, so you should get, at the end of the day, ka plus kb equals 0, or a equals minus b, and so 1 minus 1 works for a and b. So this is the vector, and c and d are related by multiplying by the eigenvalue, 1 plus 2k minus I times square root of 1 plus 2k. Okay, so we did this eigenvalue. We know the doppelganger eigenvalue with minus I. Everything's going to be the same thing, but with minus i's. We know we can convert it to cosines and sines, and if you do that, we get something we can finally interpret. So if you do that and you interpret solution, And so the solution really is this big vector with four components. But the four components, remember, are related to the positions and the velocities of the original guy. And we actually only care about the positions. So from the full solution, if you read just the first two components, that tells you the positions of everything, and that's what I'm going to do. I'm not going to look at the velocities. We know if we wanted the velocities, we could do the derivative of the positions. So what do we get? We get C1 cosine of t plus C2 cosine of t. Sine of t, okay. And this was the same thing, C1 cosine of t plus C2 sine of t. That was the first half we got. Now there's a second half with the other eigenvalue, the other frequency involving the square root. And I've written this a little bit big, so let me do a little bit of a cheat here, get my paper a little extra big. So now I need a C3 and a C4, and if you do the same thing with C3 and C4, so the top row doesn't change much. You get cosine of the square root of 2k plus 1 times t plus C4 times the sine of the square root of 2k plus 1t. Okay, but here is the important part, is that y1 and y2 in the last eigenvalue are related by a minus sign. So in this second row, it's not C3 and C4, it's minus C3 and C4. So that's important, minus C3 times the same thing. So we got this big thing, four terms, and the important thing is how are y1 and y2 related. So y1 individually looks kind of boring. It's just C1, C2, C3, C4. But the important thing is how they are related. So C1 and C2 are plus in both of them. That means the solutions are going together, and over here they're with a minus, they're going apart. And I think it's a lot easier to see what's going on if you write it in phase amplitude notation, which is what I'm going to do now. So I'm going to take the same thing, instead of doing C1 cos plus C2 sine, you write it as some amplitude A times the cosine with a phase shift. So then what do you get if you do it that way? I think this is the ultimate way to understand what's going on. A1 cosine of t plus phi 1. A1 cosine of t plus phi 1. So that's the first bit. You can condense the C1 plus C2 down into an amplitude and a phase. Okay, and the second bit, you do the same thing, and now they'll be with a plus and a minus. So A2 times the cosine of t plus phi 2. This is a different frequency. Let's square root of 2k plus 1. Should go in there. Okay, A2 Okay, so what's going on? We have these two solutions, and this part of the solution is in phase, they go together, and this part is out of phase. And we saw some animations of how this works, and I'll show you those again on Desmos. So that's up here. So there's the solution where they're in phase, that's what's being shown now. There's the solution where they're out of phase, and that one vibrates a lot faster. So right now, what I'm showing you, they're vibrating very quickly. This is the solution where A2 is non-zero, they're out of phase, and they're vibrating quickly at this frequency 2k plus 1. So A2 is non-zero, and A1 is 0 in the animation right now. So A1 is 0. And then the opposite was what I was showing you before. So if A1 is there and A2 is 0, that's the solution where they're both equal to 2, and they go slowly. And the point is, the thing to understand is that every solution under the sun, no matter what, is just some combination of these things. So if you start at a different position, you have a mixture of these two things. So that's the superposition principle in action. Everything will be a mixture of these two frequencies. So what is the moral of the story? When you have complex eigenvalues, you get these, every complex eigenvalue is some kind of oscillation. They come in pairs, and you can divide up your question into little pieces where each piece corresponds to one eigenvalue pair, 1 plus and minus I. Okay. So that's the solution for this thing. Did I have another top hat follow-up? I think I didn't. I think I'm just going to stop there. The last thing I just have here is, are there any questions? So this is a good time. I know it's a little bit less interactive than usual. It's good. I think it went well for our first try. But this is your chance to ask any questions you want in the top hat. And then I think we're going to call it a day after that. Yes, people want to see the paper. Okay, this paper ended up being 2 papers on the top here, which is part of the reason why I think the second formulation here is a little easier to work with, a little more compact. Okay, someone is asking a good question about dampers. Let me put that up. So someone is saying, since there are no dampers, is it expected that the eigenvectors are always just imaginary, as in the real part is 0? So if you look at the solution here, these solutions are both purely imaginary, and that's indeed because we had no friction. So you could imagine if instead of the mass spring system, so if we took the original mass spring system, which was 2 masses and springs like this, if somebody added some friction here, so sometimes people call this a dash pot. So if you add friction, to the middle, it won't affect the in-phase solution. So if you added friction just to this little middle piece, I think what would happen is you would get an e to the minus mu t and an e to the minus mu t coming up, but only in the second term. And the reason it's only in the second term is because this friction does not affect the in-phase solution. The in-phase solution, they go together, and so the friction will only be in the second term. And actually, I think I have that built into the demo here. So if I quit that for a sec. Oh, maybe I don't have it built into the demo. I do not have it built into the demo. I can put it in for next time. So what would happen is over time, the springs, if it had this friction, like in the picture that I've drawn here, if you have friction in the middle, over time, the out of phase component would go to 0 and they would synchronize. So they would, no matter how they started, if you waited long enough, they would eventually become in sync. And that's because friction would eat away all the energy from their out of phase term. So that's something to do. That's a good example question that can happen. Okay, what else did people say in top hat? One other really good question, why does the C3 and the C4 have a minus sign in the solution? So this minus sign came from the fact that the solutions, the eigenvectors, so this part, the first 2 parts, came from the solution where the eigenvector was 1, 1, I, with plus minus. And that means the 1, 1 is what to focus on. I only took the first 2 components out of that. So because they're both 1, 1, they were exactly the same. In the second 2 things, the eigenvector, it's the one I made you guys calculate, it's 1 minus 1, and then it was plus minus square root of 1 plus 2k I, plus minus square root of 1 plus 2k I. And so because of this 1 minus 1, the parts coming from the second eigenvector pair are minus of each other. And it really comes from this 1 minus 1 thing. I think that's where to see where do these minus signs come from. They're the fact that it's 1 and minus 1. That's the way to see it. Okay. Could you repeat what is the relationship between the in-phase and out-of-phase portions? So I wouldn't say there's a relationship between them. I would say this is its own pair, these 2 things. This is its own pair, these 2 things. And the general solution is just the linear combination of them. So it's the superposition principle. You solve them each separately, you just add them together and interpret that way. Okay, I'm going to stop there. I will put up a suggestion thing. So, this is my first time doing this kind of stream. So if you have suggestions on what could be done better or what worked or what didn't work, I'm very happy to hear them. And we'll try it again on Thursday and see how it goes. So thanks a lot for tuning in. The one problem I didn't get to was a problem from the textbook. We'll do that next time from section 6.4. So if you want to read a little bit of 6.4, you can do that. On Thursday, we're also going to start chapter 10, and there is that reading thing for you to do. So you should have plenty to keep you busy between now and Thursday. Okay, I'm going to stop there. You can always send me questions by email or whatever, or on Piazza is a great place too. Okay, I got to figure out how to turn this off, which might be fun. Okay. I found the button. All right, take care, guys.